convex, projective, polyhedral reflection rules.
Thank you. So my talk is about the definability criterion for cocompact, convex, projective, polyhedral reflection groups. So it is about the representation of compact Coxeter orbitals to SL plus minus n plus 1 R as introduced by Mr. Lee. So, introduction. Much of the introduction will be almost same as the introduction of Mr. Lee's. We work on SN, which is the two-fold cover of the real projective space, and which is the set of half-lines in the real vector space Rn plus 1. Group of projective transformations of Sn is the group Sl plus minus n plus 1 R. Linear transformations from B to B whose determinants are either 1 or minus 1. A subset omega, a subdomain omega of Sn is convex if its intersection with any gray circle is connected, and it is properly convex if moreover its closure does not contain two opposite points, and it is strictly convex if moreover its boundary does not contain any line segment of positive length. Open properly convex set omega is called divisible if the group of automorphism contains a discrete subgroup which acts properly discontinuously and cocompactly on omega, such that the quotient is compact. If gamma is such a subgroup, then we call that gamma divides omega. So I think this notion is originally from Benoit. And a discrete subgroup of SL plus minus n plus 1 R, which divides an irreducible properly convex open domain omega in Sn, is said to be irreducible convex dividing linear group. So I just named this as irreducible convex dividing linear group. Let Hn be the subset of Sn, the set of half-lines in the Lorentz cone. Qx is the corrective form, x1 square minus x2 square minus xn plus 1 square. This group of automorphisms is the group, this orthogonal group of Q which preserves this Hn. Reflection sigma is an element of order 2 of SL plus minus n plus 1 F, which is the identity on a hyperplane. So reflection can be defined on any vector space or any field. So all reflections are of the form identity minus this alpha tensor B for some alpha in linear functional and B in the vector space with alpha of B is equal to 2. And V and alpha are different from 0 and determined within a transformation by scalars. And we set the matrix Cij alpha I B J and call this matrix Cartan matrix. And product Ci1 to this IKI1, the cyclically defined, is called cyclic products. And the cyclic product is called simple if all its indices are distinct. And every cyclic product is a product of simpler cyclic products. If gamma divides an irreducible properly convex set, then gamma is completely determined by its Cartan matrix of conjugation. And hence, if gamma divides an irreducible properly convex set omega, the tuple of simplest squared product is a complete conjugation invariant of gamma. N-dimensional or structure on a second countable Hausdorff space is given by atlas of compatible charts where U is an open subset of Rn, G is a finite group acting on U, and Phi is a homeomorphism. This portion to be for an open subset V of X. So on n-dimensional or structure on an n-dimensional polyhedral P is given by giving orbifold structure on P where each point of the interior of each face has a chart marked on an open subset in Rn with a reflection acting on it. Each point of the interior of each side of codimension 2 has a chart marked on an open subset of Rn with a dihedral group generated by reflections. And there is a Wimber's result. So let P be a convex polyhedron of Sn, and for each face S of P, let sigma be a projective reflection fixing this face S. Then let gamma be the group generated by the reflections. Then the following conditions for every ST such that this codimension is equal to 2 are necessary and sufficient in order that this polyhedral P tiles some convex subset of Sn. So this is the CST is the entry of the matrix, Cartan matrix, and first one is CST is less than or greater or greater or equal to 0, and second one is greater than the product is greater than or equal to 4 or is equal to 4 cosine pi over m st squared greater than 2. So moreover, the group is discrete. The convex set is open if and only if for every x in P the group generated by this reflection sigma, whereas containing x is a finite group. So in this case, we say that gamma divides omega. There's example by Wimberg and Keck. There's an integral matrix 2 minus 1. This is a Cartan matrix of 3, 3, 4 triangle reflection group. So we can, from this Cartan matrix, we can set alpha 1, alpha 2, alpha 3, and V1, V2, V3 as follows. And then we can see that this satisfies the Wimberg condition I just introduced. So as far as we know, this is the first known Zariski-dense faithful representation of a surface group to SL3Z. There's another example. I draw the picture for 3, 4, 6 triangle group dividing strictly convex domains. This is the Cartan matrix of 3, 4, 6. You can check the Wimberg condition. -2 times -3 over 2 is 4 equal to 4 cosine pi over 3 squared, etc. So this is the picture when t is 1 over 6, when t is 1 over 3, and when t is 1 over 2, when t is 1. Turns out that this gives integral representation of this triangular reflection group. I would like to introduce the notion of definability over rings. First of all, let B be a finite dimensional vector space over a field F, and A is a subring. Set L is a set L of V is said to be on A lattice if it is a finitely generated A submodule, and the natural linear map from the tensor product FL to V is an isomorphism. And recall that the commutative ring R contained in a ring S is said to be integrally closed in S if R is equal to the integral closure of R in S. That is, every monic polynomial with coefficient in R, every root of this polynomial belongs to S, also belongs to R. Let delta be a family of linear transformations of V. An integrally closed Noetherian ring A in F is called the ring of definition for delta if V contains an A lattice that is invariant under delta. In this case, we also say that delta is definable over A. So this is the definition of definability over rings. So if A is a PID, then the fact that delta is definable over A means that there is a basis in which the transformation of delta can be written down by matrices with elements in A. If A is not a PID, this does not necessarily happen. Suppose that a non-degenerate scalar product is defined in this vector space V. The group of automorphism of V that preserve this scalar product is denoted by OV and its unimodular subgroup by SOV. There is another theorem of Wingberg. Suppose n is greater than or equal to 3, and let F be an algebraically closed field of characteristics 0. Let gamma be a Zariski dense subgroup generated by reflections. And let delta be any subgroup of finite index in gamma. Then the following properties of an integrally closed Noetherian ring A are equivalent. First one is delta is definable over A. And second one is AD delta is definable over A. AD is the adjoint representation. And third one is A contains all the simple secret product of the Cartan matrix of gamma. So this is my main result, one of my main results. Statement is similar, but the group is changed. Suppose n is greater than 2 is an integer, and f is an algebraic closed field of characters 0. Let gamma be a subgroup of SL plus minus n plus 1 f, and it's a Zariski dense generated by finitely many reflections. Let delta be any subgroup of finite index in gamma, then the following properties of an integrally closed Noetherian ring A in F are equivalent. So first one is gamma is definable over A, and A contains all the simple secret products of the Cartan matrix of gamma, and second one is delta is definable over A. There's a corollary of this. This theorem holds for any group generated by reflections in SL plus minus n plus 1 on R that divides an irreducible strictly convex open domain. So this is the sketch of proof of the theorem first. So by Wingberg, ZTR gamma is the ring with unit element generated by the simple square products. And if characteristic of F is 0, then gamma is absolutely irreducible, then integrally closed Noetherian ring in F is a ring of definition for gamma if and only if it contains ZTR gamma. So this works only when gamma contains rank 1 Z gamma contains rank 1 element, or the element of rank the rank and the element of rank which is relatively prime to I think the maximum rank gamma. So anyways, the reason here is the smallest rank of Z gamma is 1 here, since it contains the ID minus reflection. So from these two above statements, we have equivalence of 1 and 1 prime. So we call this 1 and 1 prime, and so the equivalence of 1 and 2 will be explained later. And this follows from the same kind of theorem for finite representative group, and the fact that the trace of reflection is n minus 1. So this is the trace is in Q, which is in the field of fractions of A. So this is proof of the corollary. This corollary is so this theorem holds for any group generated by reflections in SL plus minus n plus 1R that divides on irreducible strictly convex open domain. So let gamma be a discrete subgroup of SL plus minus n plus 1R that divides a strictly convex open domain Sn. So by gamma, the real Zariski closure is either the orthogonal group or the unimodular orthogonal group, if only if this omega is in hyperbolic space. Otherwise, the gamma is either, the Zariski closure of gamma is either SL plus minus n plus 1R or SL n plus 1R. So if gamma is a polyhedral reflection group which divides a strictly convex open omega, then the real Zariski closure is either O plus 1n or SL plus minus n plus 1R. Since it contains determinant minus 1 element. So the corollary follows from Bimbo result for orthogonal groups and the above theorem. So there's other result of ours. Suppose n is n greater than 2 is an integer, and let f be an algebraically closed field of characteristic 0. Let gamma be a Zariski dense subgroup generated by finitely many elements, and let delta be any subgroup of finite index in gamma. Let A be an integrally closed Noetherian ring in F, and let K be the field of fractions of A. Suppose that for this I, the reflection sigma I satisfies one of the following conditions. The order of sigma I is finite and relatively prime to n plus 1. Or the trace of this sigma I is non-zero, and in K, the field K was the field of fractions of A. Then the following properties of an integrally closed Noetherian ring A in F are equivalent. Gamma is definable over A, and delta is definable over A. Unfortunately, we don't have anything other than this. So sketch of proof. So 1 plus 1 implies 2 is obvious. So assume 2. Record that 2 is delta is definable over A. Then because delta is definable over K, which is field of fractions, then there is an invertible linear map G from Fn plus 1 to Fn plus 1, so that this Kn plus 1 is an invariant K lattice under this G delta G inverse. And by Bimbo, it is known that this 2 implies this AD delta is definable over A and AD gamma is definable over A. And we can see that this SL plus 1K Lie algebra is a K lattice of SLN plus 1F invariant under this AD G delta G inverse. And by Wimber, this SLN plus 1K is also invariant under AD G gamma G inverse. So this is by, the last step is by Wimber. And there exists the, so there is the non-zero lambda I such that this lambda I G sigma I G inverse is in GLN plus 1K. This is another lemma of this is a lemma of Greenberg, but if this is satisfied, if SL
What is G?
G is yes. So if SL plus 1K is invariant under ADG gamma G inverse, then there is the non-zero lambda I, scalar lambda I, such that this lambda I G. So this head is a matrix written in standard basis. It's in GLN plus K. And determinant of this product is just the lambda I n plus 1. And trace is lambda I times trace of this reflection. So if sigma I is of the finite order, Li, we have that this product to the Li is equal to lambda I to the Li times identity, so that this lambda I Li is in K. So if Li is this relatively prime to n plus 1, then lambda I is in K. So, and if trace of sigma I is in K, then of course lambda I is in K. So,
What is G hat? What is it?
G hat is the matrix written in standard basis. So any hat is the matrix written by standard basis. So this G hat sigma I hat G sigma G hat inverse is in SL plus minus n plus 1 K for each I. And gamma is defined over K if our condition is satisfied. So since AD gamma is definable over A and gamma is definable over K, from Wimber it follows that gamma is definable over A. One of the theorem of Wimber is that if AD gamma is definable over A and gamma is definable over K, then gamma is definable over A. So I would like to apply our result. First, for group generated by refractions. For some compact object before P, we find all or some conjugacy classes of irreducible convex dividing projective reflection groups that are definable over Z or some other ring of integers. So for the fixed O before P, we try to find out if there exists an irreducible convex dividing reflection group isomorphic to the fundamental group of P, whose cyclic products are integers. So before that, the theorem for group generated by refractions. So gamma is definable over A if and only if A contains all the simple cyclic products of the content matrix of gamma. we try to find the case when cyclic products are integers. So indeed, for simplicial or for P that admit hyperbolic structures, we can compute all the conjugacy classes of irreducible convex dividing reflection groups isomorphic to this fundamental group of P. Well, suppose that 1 over P plus 1 over Q plus 1 over R is less than 1. And let P be a PQR triangle, also told before. And the following list shows the number of conjugacy classes of irreducible convex dividing reflection groups isomorphic to this fundamental group in SL plus minus 3R that are definable over Z. So these are lists. So here, N is the number of conjugacy classes of irreducible convex dividing reflection groups isomorphic to pi 1 this fundamental group definable over Z. Proof. We give a proof just when PQR is 3, 3, 4. The other cases are similar. So let this be a Kanghyun matrix. Then by Wimber, we can choose reflection generators, sigma 1, sigma 2, and sigma 3. So that this C1 to C21, etc. satisfies Wimber condition. So this is equal to 1, 1, 2 respectively. And since the product of the C1 to C21 and C1 to C31 and C2 to C32 are equal to the product of this C1 to C23, C31 and C1 to C3 to C31, we can have only two possible different integer tuples of simplest Greek products. So possible tuples are this tuple of this product are this 2, 1, 1, 2, 1, 2, and 1, 1, 2, 2, 1. So this is equivalent to say that we can have two different equivalent classes of Kanghyun matrices whose cyclic products are integers.
Are they conjugate?
Yes.
They're not conjugate over. Are they conjugate over SL3R? Or they're not? Where are they not conjugate? SL3Z?
They are. I mean, these two when they have these two tuples of products.
The talk we just heard before this, is this saying that the deformation space has two components, or?
No.
It just said.
Just integral. We try to find integral representations here.
It's integral representations, and they're not conjugate as integral representations.
Yes.
But they probably are conjugate in SL3R.
No, they are not. They are not.
They have different cyclic products.
Yes.
If you have different cyclic products, it's not good.
Different Kanghyun matrices, but it's still oh, I see. They're still a one parameter family. Okay, never mind.
And
Let's see. Sorry.
so let P be one of tetrahedral concept before described in the figure. This figure. So they have edge orders 2, 3, 4, 2, 3D. So if D is equal to 3, then the number of conjugacy classes of the irreducible convex dividing reflection groups isomorphic to this fundamental group in SL plus 1 4R that are definable over Z is 2. So if D is 4, then the number of conjugacy classes of irreducible convex dividing reflection groups isomorphic to this fundamental group in SL plus minus 4R that are definable over Z is 3. Proof is similar in the case of triangle group. Now let P be the four-dimensional simplicial Coxeter before. This Coxeter graph is described in the figure. So then the number of conjugacy classes of irreducible convex dividing reflection groups isomorphic to pi 1 P in SL plus minus 5R that are definable over Z is 2. Proof is similar. Now suppose that this 1 over 2, 1 over Q plus 1 over R is less than 1. let P be a 2QR triangular coxetal before, then there exists a unique conjugacy class of irreducible convex dividing reflection group isomorphic to this fundamental group in SL3R. And the smallest ring of definition is generated by 4 cos square pi over Q and 4 cos square pi over R. This is just because there exists just one tuple of simple square products. It contains 2 cosine square pi over 2 is 0. And now let P be an n-dimensional simplicial coxetal before admitting a hyperbolic structure whose coxetal graph is not a tree. Let delta be a reflection holonomic group of a properly convex projective structure on P. Suppose that K is a totally real number field that is also a field of definition of gamma. Suppose that K is not in Q, not equal to Q, then there are infinitely many conjugacy classes of irreducible convex dividing reflection groups isomorphic to pi on P that are definable over the ring of integers. So if we really, I guess if there's H order 2, then there is some problem, and if there is no H order 2, then there are infinitely many conjugacy classes of irreducible convex dividing reflection groups. And there is other result for cubes and prisms. So for cubes, let T be the coxetal before denoted this CO2N1 that is described in this figure. And there are at least 3 conjugacy classes of irreducible convex dividing reflection groups in SL plus minus 4R that are definable by Z. So this is the diagram of cube. The H orders. Proof. So Mr. Gaesan Lee has computed that the dimension of this infinitesimal restricted deformation space of convex real projective structures on P is 1, and there is a 1-parameter family of conjugacy class of representations of this fundamental group of this coxetal referred to as a plus minus 4R. So based on his result, his computation, we have found that the corresponding contact matrices are given as follows, and T is here real parameter. And we tried to find the integer square products, and we found that there are only 3 of them we found here. And so only possible value of T are here 0 and minus 4 over 5 root 5 and 4 over root 5. This gives 3 different integer tuples of simple square products. So this is the example of prism. Suppose that here D is 3 or 4. And let P be a triangular prism given this figure, then the number of irreducible convex dividing reflection holonomic groups in SL plus minus 4R, which are definable with Z, is 0. Just because there are so many tools here. We would like to apply our theorems to triangle groups also. So theorem, suppose that set L1, L2, L3 satisfies one of the following properties. First one is we can choose 2 elements of L1, L2, L3 such that its chosen element is 6 or 12 or not multiple of 3. And second one is 2 is in this set. And let G, L1, L2, L3 be a triangle group as follows, and let gamma be an irreducible convex dividing linear subgroup, which is isomorphic to this triangular group. When the delta be any subgroup of finite index in gamma. The following properties of an integrally closed Noetherian ring A in F are equivalent. Gamma is definable over A and delta is definable over A. So unfortunately, we don't really have a method to find representations of these triangle groups. But we have this result for finite index subgroups. So proof, suppose first that we can choose two elements of L1 and L3 such that its chosen element is 6 or 12 or not multiple of 3. And without loss of generality, we can assume that we choose L1 and L2 and each of these is 6 or 12 or not multiple of 3. So we write gamma as gamma is equal to generality by sigma 1 and sigma 2 and sigma 1 and sigma 2 is order as L1 and L2 and their product as order L3. Then sigma 1 and sigma 2 satisfies the condition of our theorem. In particular, when L1 or L2 are 6 or 12, the trace of sigma I is in K because finite order elements in SL3R as a certain form in by up to conjugation. It has it's written down by block of rotation matrices, product of rotation matrices and identity matrices. But in this case, this rotation matrix has rotation matrix is just post data. So up to conjugation, all the matrices are this form. So if you compute traces, it's equal to 2 cos theta plus 1. So theta is this is AI and AI is relatively prime to 1. AI and order of sigma I is relatively prime to 1. So always we can, up to conjugation, we can write the finite order matrix of 3 by 3 matrix as in this form. So you can compute traces and then when Li is 6, so trace is equal to two, and when Li is 12, cosine square of this theta is in Q. So it turns out that this trace is in K is because for finite order element, 3 by 3 matrices. For finite order matrices, we have this equality. So if cos square of theta is so this is 2 cos theta plus 1 square minus 1. So this is equal to so K, remember that K is the field of fractions of A, so it contains the defining the smallest field of definition of this AD gamma. So, but this AD gamma, the smallest field of definition for AD gamma is generated by these traces of AD elements, or the trace of AD of G and G is the element of gamma. So, so if cos square of theta is in K, then cos theta is in K. So, and because trace is 2 cos theta plus 1, 2 cos theta plus 1 is in K. So, so this is correct. The problem is that when L is 3, we cannot really say anything because the trace becomes 2 cos theta plus 1 becomes 0. So we can't really say anything. And so now the result follows from our theorem for finitely generated curves. So now the second condition was, remember that one element of the set, but L1, L2, L3 is 2. And then by Goldman and Choi, the deformation space of this convex sphere projective structure is a single point. And it is known that if two convex sphere projective 2 OB4s have same fundamental groups and the fundamental group is a triangle group, then these two OB4s are homeomorphic. And it follows that there is only one SL3R conjugate class of areas of convex dividing linear group isomorphic to this L1, L2, L3 when one of Li is equal to 2. And this gamma is always contained in a areas of convex dividing L1, L2, L3 triangle reflection group, because there exists a triangle reflection group image. So as a two-index subgroup. So now the result follows from our theorem for groups generated by reflection, because this triangle group is a two-index subgroup of triangle reflection groups. So there's some comments and questions. I looked at long read and sorry, I cannot pronounce the name, but Dr. T, and it is known that there are infinitely many family of characteristic dense space representations of the triangle group G334 to SL3Z and SL3R, and this G44 is a index 3 subgroup of G334. This family of representation of G334 to SL3Z is the representation to SL3R. Both the image of G44 and 444 and G334 are in SL3Z. But can you find the Zariski dense spaceful representation of G334 in SL3R that is not in SL3Z, such that the image of the subgroup G44 is in SL3Z? Because there are two theories, we cannot use our theorem here. For 344, we can use our theorem, but for 334, we can't use our theorem. Because, there are 2 3s. And there are references. And this is alright. Prepared? Thank you.